Yes. Okay. Good afternoon to everyone. I'm happy to introduce you today's speaker, Professor G. Ambiga from XII Tirupati. Professor Ambiga is a well-known person to us. She had visited our department a couple of times earlier, and she has very long association with our department. In view of MSc students assembled here, I wish to read out Professor Ambiga's biodata in a very brief manner. She joined as an associate professor at XII Pune in the year 2006, and she became a professor in 2012. A couple of years ago, she moved to XII Tirupati. Professor Ambiga works on several topics in nonlinear dynamics, including complex networks, data analysis, modeling biological systems, and so on. She has trained a large number of students in nonlinear dynamics. You can get more information about Professor Ambiga's research works on visiting her institute homepage. With this short introduction, now I invite Professor Ambiga to deliver the talk. Over to you, madam.
Thank you, Professor Sendilvelan. I'm very happy to give this talk to the audience in Bharatdasan University and others who have joined with me, Professor Lakshmanan, and all the colleagues in Bharatdasan University. A very good afternoon. I'm always happy to connect to Bharatdasan University. As Professor Sendilvelan pointed out, not couple of times. I have visited large number of times to Bharatdasan University, especially when I was doing PhD and postdoc. I was in Cochin where there were not many journals available, and Professor Lakshmanan was very kind enough to invite me over to Bharatdasan, and I used to use all the journals there to look through the literature and understand lots of things in nonlinear dynamics. I thank Professor Lakshmanan and all the colleagues in Bharatdasan University for this. And I am very happy to note that, and in fact, I appreciate that you have taken up this initiative to have a series of lectures online. And I could see that in the last couple of months, a large number of very nice talks have happened in this series. And I could join only a few of them, but they are actually very good and very highly motivating to the students of Bharatdasan University and elsewhere. So with this, let me start sharing my screen, and then we will go ahead with the talk. Are you able to see my screen?
Yes. Yes.
I'll go to full screen. We go to full screen.
Yes.
Okay.
Perfect.
Okay. So the topic of my talk is complexity measures from data. So I will first motivate the students, and as I'm told that the majority of the audience are students, so I will briefly introduce the relevance of doing data analysis from a point of view of nonlinear dynamics and complex systems, as well as I will tell you why we want to do it and what are the interesting information that we can collect from analyzing data. So the plan of the talk is like this. I will briefly introduce the concept of using data from complex systems, and we want to look at it from a physicist point of view. So we want to understand them from a dynamical systems point of view. So the first step will be to reconstruct the dynamics from the data, and then we try to characterize and quantify the complexity of the reconstructed attractor. I will illustrate using some of the data that we have used in our analysis in all these measures. Then some of the recent trends are to look at the recurrence pattern of the trajectory that we have reconstructed. That we do using two methods. One is recurrence plots and its measures. Another is recurrence networks and its measures. Here also I will illustrate how useful they are in understanding the processes underlying astrophysical data. And we have done introduced some measures in the recurrence network like degree heterogeneity and weighted recurrence network, etc. I will briefly touch upon them. And one of the recent trends is to have multiplex recurrence network to analyze multi-channel data or multi-wavelength data. And in the end, if time permits, I will also see how this type of quantifiers and analysis can be used to understand dynamical transitions happening in such systems. And if possible, to have some early warning signals, which will tell you that some transition is going to happen in the system. So how do we study complex systems? I would say, in general, there are two major approaches. One is studying the systems based on dynamical models. And if that is possible, we can use them in the framework of complex networks. So basically, if you want to have a definition for a complex system, it is a system consisting of a large number of subsystems or units, all of them interacting with each other, but not in a regular manner, but in a very complex pattern of interaction. So the framework of complex systems is very ideal for studying them, and we assume that the collective behavior or the emergent behavior of the dynamical systems on the complex networks will give us some idea about the response of a complex system. And then we can also study transitions on networks. I am sure you had a few lectures related to these topics in the previous lecture series. Now, today we are going to talk about how to understand complex systems if only data is available. Because there are a large number of real-world complex systems for which we don't have any idea about the dynamics or the underlying dynamical processes. We also don't know the magnitude of the number of variables required or the number of parameters involved. We only have either observational data or measured data. And most often, this is actually not coming from a single variable or anything like that, sorted out data, but it's the average response. So if you have an average response like that from a complex system, how do you make sense out of it? How do you understand its dynamics? So the second one, this is the direction in which we will be proceeding in this lecture. So we are basically going to talk about observational data. And when you have observational data that come as sequence of measured data at intervals, you call it a time series. And a few examples I am showing here in astrophysical data, the intensity of star that is measured by a telescope, like the Kepler data, the radiation from astrophysical objects, it can be in any wavelength. Then we have physiological data, a large number of them, but EEG and ECG are specific examples which give you the average response of a complex system like the brain or the heart. We have economic data, which is the financial market data. That means the stock market indices or the conversion rate of currency, output of agricultural crops. These are all relevant data which we really want to analyze for useful purposes. And a huge number of data for climate data, which is rainfall data. We have rainfall data from paleoclimate data onwards. So weather data, temperature data, humidity data, then a large number of biological data like gene expression data. Very recently, we have hearing lots about the disease spreading data in the context of COVID-19. So as this biologist Sidney Brenner said in 2002, we are drowning in a sea of data and starving for knowledge. But that was in 2002. After that, lots of things have happened. Our computational facility have gone up. They have multiple algorithms have come out to deal with data. So we are far ahead, and we certainly have a way of understanding or getting some knowledge or making some intelligent guess about the dynamics of the system, or in some cases even to predict the behavior of the system using data alone. So for that, we have to calculate some measures from data, quantifiers from data, which I call as the complexity measures. So analysis of data is important for understanding most of the natural processes because we don't have a specific number of equations to model such systems because they are very complex or because we have only partial knowledge about their underlying processes. Now, as I said, the computational methods are helping us quite a lot in this. They will help us to find patterns in the data, and then these patterns can be converted to useful information. So there are algorithms already available, and when applied correctly, then we will be getting some very nice results, which we can interpret in a scientific way. Here also, if you look at the methods that are used, a large variety of methods used by people, especially in climate-related data, is statistical analysis, which comes with signal processing methods and feature recognition along with machine learning approaches, which is a recent trend. That is one approach. The other approach is the dynamical systems approach, where you have nonlinear time series analysis. So here we are looking at the reconstructed trajectory and looking at its fractal measures and other network measures. And applications are in a large variety of interdisciplinary areas: finance, weather forecasting, earthquake prediction, and there are lots of applications in engineering and communications, power transmission, etc. Now, first of all, if you look at statistical measures from data, statisticians usually consider the time series as a realization from a stochastic process, and most often with a Gaussian distribution. So they unveil the probability law from the observed time series and then compute mostly two very good quantifiers, which is the mean and the variance. But when are these two numbers meaningful? If the hypothesis that is justified that the observational data comes from a Gaussian distribution, and then this mean and variance will characterize it completely. And there are cases where there are many statistical measures which will help us to forecast future events, and then we can even use this statistical approach. But the statistical approach need not always be helpful. Then what can we do? Just to give us an example, this I have taken from this Wikipedia. There is something called, you must have heard about this Anscombe's quartet. There are 4 data sets that are nearly identical descriptive statistics like mean and variance. But see how different they are. So these two quantifiers, statistical measures alone, may not help us to understand everything about the data completely. However, even now, the first step that we do when we get a data is, of course, to do some statistical measures. As an initial step for further development, we will calculate the mean, median, standard deviation, and probability distribution. This will help us to check for stationarity in the data, which means if the mean remains almost the same over time in a long length of data, then we can say it's a stationary data. And we will use these measures also to identify some trends in data. So this is actually required as the first stage in the pre-processing of your data. But beyond that, we cannot take this in many cases because we have to look at certain other features that are present in the data. So that is where we come across this nonlinear time series analysis. So this is actually an analysis of the observational data, as I said, using a dynamical systems approach. We want to extract dynamical information about the succession of values in the data set. Here also we are looking for pattern recognition, which means we will like to highlight patterns in a data set. And we say this analysis will lead to data compression because a few characteristic measures can replace a large sample of data. So this reduced information is enough to understand about the underlying dynamics of the system. But only thing is we have to be careful how we interpret the computed measures because they have a specific meaning and they are meaningful only within some model framework. So once you know these limitations or the region where you can apply this, then we are through. So the first step in this analysis is recovering dynamics from time series data. So as we said, for most of the complex systems, we have only observational data. And this data varies in time in a non-trivial manner, which means there is an underlying dynamics. The values are changing in time, which means some of the features of the system are changing in time. So suppose we say this is produced by a dynamical process. That is why the values are changing. Whatever response of the system is changing over time. So can we get an idea about that dynamics so that we can recreate the dynamics from the data? So once you have, this is the first step. And once you have done that, we study their complexity. We can study dynamical transitions. We can compare similar dynamical systems. We can model the dynamics if possible. There are specific cases where even the differential equation representing the system could be derived at using this process, but they are limited situations. But sometimes it may be possible even to make some predictions. So this branch we call as data-driven dynamics, where we are reconstructing data from the dynamics from the data. So when we say reconstructing the data, as we understand a dynamical system, we have a phase space. In this context, many people call it a state space because it is slightly different from the phase space that you talk about in the Hamiltonian system. Here we are not restricted by having dynamical variables like position or velocity or momentum, etc. Dynamical variables can be anything that changes in time. It can be a temperature, it can be an angle, it can be pressure, anything that varies with time we will call as a dynamical variable of the system. Then we construct its dynamics or trajectory in a state space and then analyze the structure of the trajectory. That's what we normally do. So just to give you an example, in a way, this is actually a reverse process. You are given the output, then you want to say what is a system that is producing this data. So take a simple example of a harmonic oscillator. You are given the time series of a harmonic oscillator as a function of time, this x variable, let us say. So we know that a harmonic oscillator has a periodicity and therefore the output is something like a sine wave with a given periodicity. So we can say that if we are given this and you are asked to find out what is the system of equations that can produce this data, you will immediately say that we can write an equation like this, either x double dot equal to plus omega 0 square x equal to 0, or you can write it as a two-dimensional system where x1 dot, which is the velocity, is x2. Then we can say if you integrate this system for any given value of omega 0, you can get an output like this. Now, just because we get an output like this, we cannot always say that this is the system. This is not unique when you go backwards or in the reverse way. Because look at this data. This is actually coming from a forced damped harmonic oscillator. So it also gives almost the same type. Only thing is frequency need not be the same. However, the periodic behavior is the same. So this is the forced damped harmonic oscillator, which you can write as a three-dimensional system like this. So and it can produce an output like this. So given this output alone or the time series alone, it's not possible to predict whether these are coming from this system or this system. Now even little more complicated case here, look at this time series. This is actually coming from an system of equations like this, which is actually a nonlinear dynamical system. So if the behavior is exactly periodic, even nonlinear dynamical systems have periodic behavior for certain parameter values, then the time series of one of the variables, looking at that alone, we cannot go reverse and then say which is exactly the system from which it comes. And I am sure all of you are familiar with this attractor, periodic attractor of a Duffing oscillator. It has a time series like this. So we know that this is the time series of this. When you have this trajectory, we know that this is the output. And if you have an output like this, we know that, of course, this is not a periodic output at all. And there are ways to detect whether it is chaotic or not, which I am sure most of you must have done. So this is again the output from a Duffing oscillator, which is in the chaotic phase when the parameters correspond to a chaotic attractor. But if you compare these two cases, this and this, at least we can make sense and say that certainly this is not periodic, but this is periodic. That much we can say. But look at these two time series, two typical cases, one shown here, one shown here. Visually, if you look at it, they look almost the same. But this is generated by this attractor, which I am sure most of you will know. This is from a Henon map. And on the other hand, this is produced by a Gaussian white noise like this. So that means just by looking at the data alone, especially when you have data coming from a nonlinear dynamical system or a complex system consisting of large number of systems, it's impossible to understand what is the exact dynamical equations. But to some extent, we can have some idea about its dynamics. So before we go into that, I will show you a few cases where you have some real world data, which are extremely complicated. This is from a variable star. So the star, as in time, it will be expanding and contracting because of the balance between the gravitational forces and the temperature and other turbulence inside it. And this is the type of measured values that you have for the magnitude of the star. So look at this. If by looking at this itself, we cannot say anything about the data. These are two different stars, variable stars called SU Tauri and R Scuti. So there is a pattern, that's all. Beyond that, it is difficult for us to say anything more about the data. And you must have heard about binary stars, which is a system of stars revolving about a common center of mass. So because both of them are moving like this, if you look at the intensity that is coming from one of them, certainly it won't be, even though they look almost periodic, it may not be periodic because they will eclipse each other. So when one of them comes in front of the other, there is a dip. And their variations are not because of this eclipsing alone. The processes inside the stars are so complex that there are other types of variations also happening. And even among binary stars, there are different types: detached, semi-detached, overcontact, ellipsoidal. And how will you differentiate between them or classify them based on their data? For example, if you look at the intensity coming from semi-detached, overcontact, and ellipsoid, these are some of the typical light curves that we get from these binary stars. So given these light curves alone, can we say which one is semi-detached, which one is ellipsoidal or overcontact? At least that much, even though we cannot write equations for them. These are some of the questions that we ask. And talking about data, as I said in the beginning, there are a large variety of useful data. This is the global temperature changes. We talk about global warming. So when do you think warming started? Is there a characteristic pattern in that? All these are some interesting questions. This is EEG data from a healthy person and from an epileptic patient. So how do you understand when the person is going to have an epileptic seizure? or what is the difference in the underlying dynamics for an epileptic person and a normal person. For example, this is ECG data. This is a person having a congestive heart failure, heart disorder, and this is a normal heart. So looking at it, we should be able to have some quantifiers which will help us to identify them. These are actually financial data. This is the stock market indices from some markets which are shown here. And there is a lot of interest and money that goes into understanding the behavior of these stock markets, especially we had a financial crisis in 2008. So can we predict whether the values are going to up or going to go down? These are questions they ask, and they want values in microseconds. So analyzing the data in this context is very important and money fetching. And think of any type of data: number of hospital admissions, average level of sulfur dioxide, rainfall in one particular city. And this is a very interesting data. Today I got it from the WHO dashboard. This is up to January 8th, I think. Global cases. So people talk about first wave, second wave, all these things. But can we say anything more than that? And this is the context of India. So first wave and second wave are very clear, and hopefully this wave should not go up much. That is the one just started now. So this is also an interesting type of data from which we can see whether anything can be done about them. So these are all very complex data. So highly irregular with no evident periodicity. But in some cases, there might be some underlying periodicity which you can understand by taking the power spectrum. But in general, we say there is no evident periodicity in any of them. The reason may be these systems are also highly complex. The underlying dynamics is also complex. Moreover, there can be noise added to it. The noise can come from measurement. It can come from the stochastic processes inside the system. So noise may be inherent. Noise can be of different types: colored noise, white noise, etc. So these are all added complications that can come across, that you have to come across when you analyze the data. So with all this, we will try to see how to get some complexity measures, how to do some transitions, understand some transitions by doing a sliding window analysis. And some of the recent trends are to use these measures for feature identification along with machine learning algorithms. As I said in the beginning, when you get your data, the first thing is to do some pre-processing. The one pre-processing is to rescale the data. For example, if you want to compare different types of data sets, we have to normalize all of them to the same interval. So that can be done very easily by a simple scaling like this. And most often we bin the data. This binning is done basically to avoid these unequal time steps of the data, because there can be some gaps in the data and there can be some noise. To some extent, noise can also be avoided by binning. So by binning, what you do is we take a small bin in time and average all the values within that bin and replace that with that value. So this is what is called binning. And the data normally can have some trend. The trend can be a linear trend, it can be a polynomial trend, or it can be a periodic trend. So all these trends we want to avoid, because after removing them only, we can look at the complex dynamics underlying them. So detrending is the process which we do for removing the trend from the time series. So to find out whether there is a trend, what we usually do is, as I said in the beginning, we do a statistical mean over time. And trend is not desirable because it can mask all the relevant information. So detrending for linear or quadratic or polynomial trends we do in one way, and to remove the periodic trends, we will do a Fourier transform and do some filtering. So I'm just showing, I'm not going to details of these algorithms, but I'm showing some data with which you can understand what I mean by detrending. So this is actually fitting a polynomial to the time series by least square method. The degree of the polynomial you can decide by trial and error or by optimizing the error. And then that polynomial is subtracted from the data to get the detrended data. So this is actually values of the stock market indices, which I showed earlier. This is the blue curve is the one before detrending, and this is the one after detrending. So it's clear that the major trend is removed, but all the minor and finer variations, which gives you the underlying complex dynamics, they are all retained. They are not removed. This is what we want. So general trend is removed, retaining all the other features which are in the data. And if you have a strong periodicity in the data, that also has to be removed. As an example, I am taking the case of temperature data, and this is filtered data and Mumbai temperature data over a period of time. So we check for frequencies in the data, very strong frequencies in the data by using the fast Fourier transform of the data. So this being temperature data, there is a strong periodicity around 1 year, that is 365 days, which we don't want because this strong periodicity can mask the other information. So we remove that. Also, these minor, small peaks are actually due to inherent noise in the system. So we remove both and then we get a data like this. So this is the filtered data after removing the major trends in the data. And periodic trends can also be removed by fitting a multi-periodic fit like that, where these frequencies correspond to all the prominent peaks in the Fourier transform. Then we make a multi-periodic function like this and subtract it from the original data to get a residual data. And we do our analysis on the residual data. So this is the data that we use for reconstructing the dynamics. So this dynamics is reconstructed by embedding it on a phase space. So this sampled data is used with the minimum required dimension, but we have no a priori knowledge about the dimension. However, we use the Reuel-Takens theorem, and if we are able to get the dimension properly and the delay, this is called the time delay embedding, because we split up a sequence of data into some vectors using a delay time. So once we get these two properly, because these depend upon each data, values can be different for different data. Once you do that, then there is a one-to-one mapping of points from the original dynamical attractor of the system and the reconstructed attractor. So proper embedding will ensure that we have the geometric and dynamical properties preserved, all the dynamical invariants are all preserved. So this is the process of Reuel-Takens embedding. We start with a scalar time series. That means you have a series of data at time intervals which are given. Then we construct a space of dimension m with delay vectors with delay time tau. So this is for if you have for ith time, we have this as the first component, this is the second component, and this is the mth component of the vector. So in an m-dimensional space, we are just sequentially splitting this scalar time series into vectors. But the success of the method depends on the choice of a proper delay and the choice of a dimension. So for this, there are many methods available. In fact, there are books on time series analysis by Kunz and Schreiber. And also, there are several papers available. So I'm not going to details. I will tell you one way of doing it. So the problem with delay is it has to be large enough so that the attractor points do not overlap. If the delay is very small, the coordinates st and st plus tau will not be independent enough. And therefore, the attractor will be lying along a diagonal, as I show here. This I am showing for the Rosler system as an example. So this is something we don't want because then the attractor is not properly resolved. If the delay is large, then they tend to become random because all the relevant correlations in the data will be lost and then we get a set of random points. That's also not required. So if you choose a proper delay, you will see that you are getting the proper attractor. So how do you ensure it for a given data? For this, we calculate the autocorrelation function C of t with a delay tau using this usual formula for correlation. So xn is correct and its correlation with xn plus tau. So this is the delay. This we calculate for different delay values. And for each value, the correlation sum that we get is plotted. And for example, if the delay is tau is 0, we should get it as 1 because we are taking xn with xn. But then it decreases. So the value of tau at which it reduces to 1 by e of its starting value, that point we take to be the proper delay that has to be used. So that is settled. Now, how do we choose a dimension? So there are many methods to choose a dimension. One interesting thing is most of the measures that we calculate will saturate as you go on increasing the dimension. So if they saturate, then we say that, okay, then you don't have to increase the dimension beyond that. Because increasing the dimension is at the expense of data. Because when you have a large dimension chosen, then the number of points required in the data to have a relevant number of trajectory points will be very large. Most often these data that we get are not that large in the size. So we want to have the minimum required dimension. So how do you get that? So I will explain the concept first in a very simple way. Suppose we have a 3-dimensional system and we are projecting it into 2 dimensions. And then the points which are actually separated in the 3rd dimension will lie close together in the 2-dimensional projection. So which means if you have taken a dimension m, which is not the required dimension, which is less than the required dimension of the system, then the points which are close together may not be actually close in a higher dimension, which is m plus 1. So those neighbors are called false neighbors. So how do you estimate them? We locate each point and take its distance with the nearest point, this distance, in the dimension m. Now increase the dimension to m plus 1, again take the distance. And then we take a measure for the difference between these two distances like this. And if this measure is larger than some value, then say the neighbor is false, which means if you go to a higher dimension, these 2 points which look close in the lower dimension will move apart. So they are not actually neighbors. So we go on doing this till we find the fraction of false neighbors reduces to 0. Then that means further increase in dimension will not change the distances very much. So we are okay to have this dimension that we get for that. So I'm showing this for a Rosler system. As you can see, these points here. This is the fraction of false nearest neighbors, and this is the increasing dimension. So we can see that as we increase up to 3, this value goes almost to 0. At 4, it is 0. And on the other hand, if you have white noise, they will not do it. So because of this, we can understand what is the minimum required dimension. This is only one method. There are several methods. Again, I am showing this for the Rosler data. This is the Rosler time series. And as we said, for every point, we get the next point, same color I have shown. This is the second component of this. For this point, this is the second component like that. And then in 2 dimensions, if you are plotting, xt is one axis and xt plus tau is the other axis, and you get a trajectory like this. And if you go on doing it for a large number of points, you can connect all of them, and then you get the trajectory of the Rosler system. So this we can see is very close to the actual trajectory. This is the actual trajectory of the Lorentz system, and this is the reconstructed trajectory. So even though every point here in one particular time may not match with every point here, but statistically the distribution of points are the same, and therefore all the measures computed will give us some sensible result. Now that we have constructed the trajectory, how do you measure its complexity? So complexity can be measured in different ways. Geometric characterization, that is the only one I am going to discuss today, but there can be a dynamical characterization also. So geometric characterization basically comes from the fractal nature of the trajectory, which means the distribution of points on the trajectory that we have got by reconstructing, they are not uniform. So some places it will be very concentrated, some places it will be very separated, and we want to look at how this distribution change over some scales. From that you can get some fractal measures. And also any bounded system will recur in time. That means it will visit the same region of the state space again and again. So this recurrence pattern is also characteristic of the underlying dynamics of the system. So this is characterized using recurrence plot and recurrence network, which I will discuss very soon. So first let us look at how do we measure a fractal dimension. There are several fractal dimensions. I am talking only about one of them, which is the most popular when analyzing time series. That is called the correlation dimension. So for any given point, what we do is we look at how many points are within a distance r of that point. That is called Ni. So this is the Heaviside step function. Since I am in full screen mode, if there are questions I may not see, shall I go ahead?
Please,
No?
madam. You go ahead, madam.
Yeah.
You go ahead.
Okay. And then we calculate a probability Pi of r like Ni by n minus 1. And it's averaged over all the number of points in the trajectory. This is called the correlation sum. Now, how does this correlation scale with r? Because if you change this r here, then of course this number is going to change, because if you make a r large, more and more points will be closer to this. So that will change. So we say that there is a scaling, or there is a dependence for this correlation sum on this distance r that you choose. And that scaling index here is a sensible dimension called a correlation dimension. It is one of the fractal dimensions of the system. So for a given data, after reconstructing the trajectory, you can compute this numerically, get this, then take the logarithm of C of r versus logarithm of r, because you want to find out this index. So you repeat this for several values of r, then plot them logarithmically, fit a straight line to that, and take the slope here. Because logarithm of CR divided by logarithm of R is the dimension D2. This is one of the dimensions that we usually calculate. So I'll just illustrate it using a figure here, because if you have a regular trajectory like this, even if this is the distance r that we are talking about, we are considering circles of increasing r. And there's a systematic way in which this number of points within that circle will increase. So if you take r here and n of r here, you see it increases r 2, 4, 8 like that. On the other hand, if you have a fractal trajectory or a chaotic trajectory, then as you go on increasing this r, it's not systematically changing in that way, because it is 15 first, then 42, 138, etc. Still, there is a scaling that you can find out, but that number will not be a full number as in this case, but it will be a fraction. That is your correlation dimension. Now, the trajectory points are not uniformly distributed. Moreover, the scaling index itself is not the same over the whole trajectory. So the value of D2 that you get at one point may not be the same as the value that you get in another point on the same system's trajectory. So that means different regions have different scaling indices. So overall, if you want to characterize all of them, we have to define a set of dimensions called the generalized dimensions. So we divide the trajectory in the boxes of size r, as we have shown circles earlier, but it can be boxes of size r, and calculate the number of occupied boxes. And then we calculate the number of points in the ith box. That gives you the probability for a point to fall in a box, in the ith box. Then this probability raised to some number q. Then it's this formula, logarithm of that sum divided by logarithm of r, in a way tells you how the scaling happens, and this is the generalized dimension. So in general, for a complex system, q can vary all the way from minus infinity to plus infinity, but positive values will take care of concentrated regions, while negative values will take care of very less concentrated regions. And most often in practical situations, you need not go all the way from minus infinity to plus infinity. It will saturate after some time. So I'm showing some example here. You can see that the points is fitted with a curve. So after some value of q, if this is almost saturated, so we know that we don't have to go beyond 10 and beyond minus 1. So from this, we can calculate the generalized dimensions. Now, there is another analogous approach to characterize such a complexity using a multifractal analysis. So here what we do is, once you have got this probability, directly we look at how this probability scales with r. So if you change r, this number probability will change. Therefore, with respect to r, we can say there is a scaling index. So, and over the attractor, there may be a large number of boxes which have the same scaling index. So we calculate that number which have the same scaling index between alpha and alpha plus d alpha, and that number will scale with r in a way which is given by a function of alpha, f of alpha here. So this alpha and f of alpha together define what we call as the multifractal measure of the system. So there's a spectrum of alpha values. That means a range of alpha values. For each alpha value, there's a corresponding f of alpha value. And if you plot all of them, you get a convex curve like this, which is called the f alpha spectrum. And there is a relation connecting these generalized dimensions and f alpha spectrum, which is a Legendre transformation like this. I'm not going into details, but using this information, given the multifractal spectrum from a given data, we can show that there can be 4 quantifiers which will characterize this multifractal spectrum uniquely. So this we have done in this paper shown here. We fit that shape of that convex function using this alpha minimum, that's the minimum value of alpha, this is the maximum value, and sorry, this is gamma 2, gamma 1, and here gamma 2. So they lie between a range. So these alpha max, alpha min, and gamma 1, gamma 2 are the 4 quantifiers which can quantify the complexity of the system. I'll just quickly go through some examples. This is actually the light curves from a black hole system. This is X-ray variability data. So spectroscopic classification tells us that there are 12 such classifications possible based on the nature of the data. So we have done some work on this, and we have shown that they can be reduced to 3 classes, because one class is nonlinear and chaotic, the other is dominated by noise, the other is purely stochastic. So this type of classifications are possible from the range of values of alpha 1, alpha 2. So that in a way defines the complexity, because alpha max minus alpha min gives you the range of scaling indices required. So if that is very small and that is single one, that means it is not at all complex. But that range becomes large means the system is more and more complex. So this is one way of doing it. That is what I am showing here. And We can use the same thing to quantify the complexity in ECG data. This is another work where we have analyzed some 32 healthy data and 92 unhealthy cases. This is how we did the detrending there. And these are the multifractal curves for them. So as you can see, the healthy ones follow a pattern like this. The unhealthy certainly is slightly different, but it's not enough if you say slightly different. We have to quantify it. So we calculate the indices. And as I said, alpha 2 minus alpha 1, which is alpha max minus alpha 1 actually, alpha min, that range of scaling indices, they have a distribution which is different from healthy people and different for unhealthy people. So this is actually from the 6 channels of ECG. Each one is from one channel. This V1 to V6 give the 6 channels of ECG. So you get some idea how these values are lying for healthy people and unhealthy people. We can do a better way of plotting them in a parameter plane of alpha 1 and gamma 1. Then you see that all these red ones corresponding to disease form one region, the green one forms another region. And if you use a machine learning algorithm called support vector clustering algorithm, you can cluster these values using their properties or range of values. And then we see that they fall into 2 different places in this parameter plane. So this can be used for identifying them. And when you identify a set of values like this using a given set of data, the challenging thing is to check whether an unseen data we can predict with accuracy. So for that, you use that unseen data as a blind data and then find out the success rate. So for this, we have to train the algorithm. We will split the available data into 2 sets, training set and test set. Use the training set and then calculate the success rate from the test set. So once we have done that, we can actually see what is the accuracy of our method depending upon the training size. So we see that there is lots of accuracy we can see from each channel like this. So this is also part of this machine learning algorithm. When you put it to that, you can do that. One more thing that we can say is the ECG data for one person, whether healthy or unhealthy, that itself is really complicated and complex. So there is no meaning in comparing one person's ECG with another person because of age, gender, so many other factors make it different even among healthy people. So how do we even find out whether there is anything that tells us? Because a healthy person's ECG may differ from another person's ECG even when both of them are healthy. So what we do is we try to compare an ECG with itself. For that, what we do is, this is a finer level of analysis where we are calculating the multifractal measures by making data, beat replicated data. That means we take every beat of ECG, make one data out of it, then another beat, make another data. So in a way, how the complexity varies within the same data, that is what we are analyzing. So this is called complexity variability, which is a better quantifier than the complexity measure itself. So this is what we are showing here. Earlier, I have shown the distribution from the full data. Now, if you do this beat replicated data, you see the disease ones separate out very well from the non-healthy ones. So you find that this can therefore be a better quantifier. These are some of the paper reports on that. Now, in the case of multifractals, I will show results of one more set of data, which is a climate data. So here we are using the climate data from this site, where we get the temperature and the relative humidity from 17 stations across India with a grid size of this much. So this is actually spatially also it is varying. We are taking all of them and then calculating. So for detrending, we use this periodic detrending or filtering and then calculate the generalized dimensions and the multifractal measures. So humidity data, these are the multifractal measures that we are getting. This is from temperature data. And what is interesting is if you apply a clustering algorithm here, we can actually cluster these 15 stations into 6 groups. So basically, this tells us that even though actual values of temperature and humidity can range from place to place, and depending upon their geographical locations, the underlying pattern of variation has some similarity, and using that similarity, we can cluster them. So in a way, we can say this will then fall into some type of climatic zones, etc. This is from the humidity data. And this is the same thing that we are getting from the temperature data. Here also we are able to classify them based on the variations. So understanding the dynamics is one thing, and then using them to doing a classification based on some k-means clustering or support vector clustering. These are all algorithms which you can use for clustering. so that you pick up which are the data sets which have some underlying similarity in its dynamics. Like that, we can classify them. So this is also one way of understanding, either for separating healthy from unhealthy or for identifying various zones in climate. These are some of the applications where we can use it. Now I come to the second part of my talk where we will talk about the recurrence pattern. So this recurrence plot is one way of capturing the pattern of recurrences of a dynamical system. So first we take the dynamic data given, construct the trajectory out of it. These are the trajectory points. And then we check how these points are recurring. After what time they are recurring is not very relevant for us, but if at all they are recurring, we want to find out that. So recurrence means the point in the trajectory should return to the state of an earlier point within some distance, because they cannot exactly repeat, because these are not periodic systems we are thinking about. So because of that, they will not exactly repeat. However, they can come close to that earlier point. Then we say they are recurring. So this neighborhood is defined by a value epsilon, which you have to choose carefully. And then we find out that xi and xj, they are points which are falling within this. That means they have recurred. Then we give an index rij as equal to 1 if they are within that. That means theta is the Heaviside function gives you a value 1. Otherwise, we give a 0. So we are now replacing the recurrence pattern by zeros and ones, totally binary. If at all they are close together, there is one value given as 1, and if they are not, value is given as 0. Now, to have a visual understanding of that, we can plot it. So these are the points in the time series on the x-axis, the same points in the y-axis, and if they are recurring and the value is 1, then we give it a color which is red. So which means if you have a totally periodic system, that should give you lines like this which are separated, equally separated, which is the periodicity of the system. But if you have a nonlinear system, you will get a pattern like this. And if you have white noise, it will be totally random points like this. This is for colored noise, which has some structure in time. So this is a visual display of the recurrence pattern. And from this visual display, we can use some quantifiers. Here I am showing the same pattern that we get for one particular solar wind speed data from a complex system like that. Here also we see there are some patterns, and we want to find out or calculate some quantifiers from this pattern. So there are many ways of quantifying them, because single isolated points means random. If periodicity or quasi-periodicity, they are separated diagonal lines. And if they are chaotic, then there will be small length of lines followed by points. So how do we quantify them? One way of quantifying is to calculate the number of dots which are there, and then look at the number of vertical lines and diagonal lines in the pattern. I'll go to that formula. This is called the recurrence rate. That means out of the whole number of points, total n squared points, how many are having value 1, means how many are recurring. So that you get by summing over Rij, and the average value is 1 by n squared. So this is called the recurrence rate. And then the recurrence points will normally form some diagonal lines. For example, for periodic system, we get exact full diagonal lines. But for other systems, the different lengths are there for the diagonal lines. So we find out the distribution of these lengths. And then from that, we calculate a measure called determinism using this. So we get the average here. P of L gives you the distribution or the histogram of the number of diagonal lines of different lengths L. And then we can also do a laminarity where we calculate the vertical lines. The diagonal lines is giving you one, vertical lines is giving you another. Its distribution, that is called the laminarity, because having vertical lines means that the system is spending a lot of time in same neighborhood in time. That means there is some sort of a laminarity in the system. So that is being captured by this measure. Now this is simple way of doing it, simple recurrence plot. When you deal with large number of data sets, there are other modern trends called the cross recurrence plot, joint recurrence plot, etc. The PIX group here in Potsdam is doing a large number of work on that. This is their site. They are actually giving all the algorithms there for recurrence quantification. If you are interested, you can look up that. Now we come to recurrence network. So once you have constructed a recurrence plot, then constructing recurrence network is very easy, because again we are going to construct a network out of the recurrence measures that you have. So I'll quickly explain how we do that. So from the matrix Rij, which was the matrix of zeros and ones that you calculated here. So this is the recurrence matrix. So the only difference is in the recurrence matrix, we did not avoid Xi and Xi, the same one coming together, because of which we have a strong diagonal line here. But when you construct a network out of it, we don't want any self links in the network, so we remove that. Then you get the adjacency matrix. So we can define an adjacency matrix which gives you the type of connections in the network as equal to 1 if the distance that we said earlier is less than an epsilon, or equal to 0 if it is more than that. And we keep these diagonal values aii equal to 1. So let us have look at this figure. So if this is your time series, let us say these are the points in the time series. First we embed them. So if you are embedding them in a two-dimensional phase, it is xt and xt plus tau. Then these are the points that you get in the embedded space, these y values. Now, for any point like y1, so look at y1, how many points are close to this? This is y1. So within a distance epsilon, we find that we have y2, y5 and y9. So from y1, we make connections to y9, y2 and then y5. That's what we do. So we find that these are the links that are generated. So from them, and by doing this, we go on constructing and we get the adjacency matrix. But here also, the crucial parameters are this choice of epsilon, because if your epsilon is very large, what will happen is there will be large number of links, because of which it's very difficult to get any meaningful information. And if epsilon is very small, the points may not get even connected. So one way of understanding this is go on increasing epsilon until you find that all the points become a single network, something like a percolation threshold. That will give you a lower bound. An upper bound means we have to make use of some other way of checking it. There are methods of doing it, which is given in this paper, where we can put an upper bound also. For example, I am showing it here for the Lorentz system. So as you go on increasing the value of epsilon, you see how they become singly connected. So initially, for a low value of epsilon, we have points which are separated or separated networks. They are forming different clusters. Now you go on increasing epsilon and you find here almost all of them are connected. But if you further increase it, there are large number of extra links coming, and then structure of these earlier links get masked. So we will not be able to understand much. And from the network, we can use most of the usual complex network measures. I'm not going into details. Most of you must be familiar with the measures like the degree of a network, of a node in a network, which you can calculate from the adjacency matrix like this. And the degree distribution is characteristic of a complex network. That also we can calculate. And there is another measure called average path length and characteristic path length, which are actually is the average of the shortest paths between every pair of points in the network. And then we calculate the clustering coefficient using this expression. This tells you for every point, how many of its points are also connected. So we look for closed triangles in the neighborhood of every ith point, and then calculate this clustering coefficient and take the average clustering coefficient for the whole network. So these are some of the quantifiers or measures which will give you some idea about the complexity of a network. All these can be exactly taken over to the recurrence network also. So I'll show you with some examples. These are some of the light curves of the variable stars which we discussed earlier. These numbers refer to the Kepler data sets. So we can see that when you generate the phase space out of it, there is very difficult to say at this stage how different they are, etc. So this is the phase space trajectories that we get. And now we construct the network out of it. You see, each one has a different type of structure for the network. We are using the same dimension and same epsilon value and same number of points. And then we find that from the structure itself, we can understand the difference between all these systems. And we can use these average values or measures that we calculate, the average degree, the CPL value or the characteristic path length or CC value. And then we can relate it to some of the astrophysical parameters itself, like the periodicity, the metallicity, etc. So we are able to find out how the underlying dynamics is connected to some of the astrophysical properties. This is possible. Again, talking about these binary stars, we talked about different types of binary stars and their data. Now we are trying to get the trajectory constructed out of it, you see there is difference in the trajectory, and the networks are also very different when you calculate the networks. So each one is very different, and therefore their measures are also different. And if you plot all these measures in a parameter plane of CPL versus CC, that means characteristic path length along this axis and clustering coefficient along this axis, you can see that using some clustering algorithm like this, you can separate out them. So that means if you are now given a data, blind data, you can calculate these measures and find out its location in this space. Then we can say whether it belongs to overcontact or to ellipsoid. Similarly, overcontact and semi-detached. So this type of classifications are possible. Not only for classifying data or understanding the complexity of data, some of these measures are extremely useful when you apply to fundamental dynamical systems also. Normally, we don't do that because for dynamical systems, we can always integrate. Given the dynamical equations, you can integrate them. And then we know we can calculate the usual measures like Lyapunov exponent. From that, we know even bifurcation structure can be calculated because we have the equations with us. We only have to change the parameter and see what happens to the system. However, just to indicate how useful these measures are, I'm just showing one example. This is the Mackay-Glass system, which is a time delay system given by this equation. And it has a transition from chaos to hyperchaos. So we can see that there is a transition for Lyapunov exponent from to hyperchaos here because two values of Lyapunov exponent, the second Lyapunov exponent only I'm showing here. So first Lyapunov exponent positive means it is chaos. The second also becomes positive means it is hyperchaos because two Lyapunov exponents are positive. So this is the one. So you see that at some value of the time delay is the parameter here, you see it crosses. Exactly the same value, you find that your network measures are also crossing. So CC increases, CPL changes. So from this also, the dynamical transitions in the system. So fundamental systems also can be understood using this. Now I will quickly tell you some of the measures that we have introduced to find out the complexity of a recurrence network. One is called the degree heterogeneity. So if you have a regular network, all the nodes have the same degree. That's a homogeneous network. So if you plot the degree distribution, it has a delta function at that value. However, most of the complex networks are not regular. They have different types of degree distributions. So the heterogeneity in the degree can be indexed by a measure which we define like this. This is the minimum degree, this is the maximum degree, and P of k is the degree distribution. And if you have a completely heterogeneous network, which means no degree is repeated, then we can have a measure, we can have the same measure for that, which we call as H heterogeneous. And then we find that for any given n, this can be reduced to this form. And for large n, it can be approximated like this. And we define heterogeneity measure for any network as its heterogeneity index divided by the heterogeneity of a completely heterogeneous network. So it is scaled with respect to the completely heterogeneous network. That gives you a heterogeneity measure. So this is something which you can use to classify systems, to understand systems. I am showing it for a protein network and for a power grid network, how this degree distribution, from the degree distribution, you calculate these measures, and that is another way of quantifying the system. And another trend that we have introduced is to construct a weighted recurrence network out of the recurrence network. So a weight factor is defined using a link between two nodes I and j. So we are giving the weight to the link connecting the nodes I and j using this relation, where ki and kij are the degrees of the two nodes I and j. And we take the strength of a node I as the sum of all these over all the links that it has. And we then say a weighted link density, and then we can have a normalized strength distribution. Just like degree distribution, we talk about a strength distribution, which is defined like this. And then from the strength distribution, we can differentiate between different systems. For example, a chaotic system, if you plot it like this logarithmically, we can say that the strength distribution can be approximated by an exponential part and a part like Sn raised to gamma. This index here will specify that this is not a noise or total white noise, because for a white noise, it has only the exponential part. This other part is not there. And we can actually differentiate between different types of noise, white noise, 1/f noise, etc. And when you change the dimension, then we find that for different dimensions, these separate while these do not. That's also one way of differentiating them. And subtle differences between quasi-periodicity and strange non-chaos all this we can make out from this strength distribution, which is very interesting. Again, for fundamental nonlinear systems, we can understand them. And just like we define a clustering coefficient normally for a network, we can define a weighted clustering coefficient using the strengths of these nodes like this. And we can also define a characteristic weight in the place of a characteristic path length, because here every link is given a weight instead of this length. So using this formula, it's a geometric formula like this, you can calculate a characteristic weight for a system. And using this plane, we can identify the locations and other things, just like we do normally for the network measures. So instead of CPL CC, we have CW and CCW here. So this is also one way of doing it. Now I will indicate a few more results that we have for ECG data, where we use the framework of recurrence networks. The earlier results I showed was on multifractal measures from ECG data. Now we see how we can use recurrence network. One basic advantage between the two approaches is that, this is a practical advantage, is that multifractal measures require a large size of the data. Unless we have large length of data available, because they are statistical measures on the trajectory points itself. On the other hand, when you construct a network out of it, even with small size data like 2000 or even sometimes 1000 values only, you get good enough statistical measures, because these measures are now on the links connecting the points. So even when you have only n points, you can have a large number of links connecting those n points when you construct the network. So therefore, if you have only the ECG data for 1 minute, mostly clinical data is always like that, unless you go for Holter data. Normal clinical data of ECG is only of duration of 1 minute. So in such cases, it is better to use the recurrence network approach, because then you don't need worry for the size of the data. So this is just showing some disease cases. This is bundle branch, cardiomyopathy, dysrhythmia, then this is healthy case, and this is myocardial infarction. Now these are the reconstructed attractors of these disease cases, some typical cases. So here itself we can see how they are different compared to the healthy case. So we can make sense out of this by computing some measures. This is the recurrence network constructed from them. From each case I am showing the same notations are used. And then as we can see, we are calculating the CP and the average path length and the link density. And here we are comparing it with noise, Rosler system like a typical chaotic system, and a typical hyperchaotic system like the XII system. So we can see what is the nature of the dynamics underlying these systems. And one more interesting thing that we find is the degree distribution of the recurrence network that we get from the ECG data has a bimodal nature, unlike the degree distribution of many complex networks. You can see that any color you check here, it has two modes. It's bimodal, green here like this. For each case, it is like that. On the other hand, for the XII system and for the Rosler system, it is only a single peak. That means unimodal distribution. So this is some interesting result which must be coming from the type of structure in the trajectory, because if you look at this trajectory, you see a set of points within this neighborhood and then another one here. So there are two spatial scales involved in the trajectory itself in all cases. That is being captured by the degree distribution of the corresponding recurrence network. This is an interesting result. Now, one more thing is, we find the link density is actually having a typical scaling with the increase in the epsilon value, because we said that epsilon is the recurrence threshold that we use. So if you increase epsilon, the number of links should increase, certainly, because more and more points can get connected because they fall within that larger value of epsilon. However, how they increase, that depends upon the specific pattern of distribution of points on its trajectory. So this is also typical to every system. So we capture that by increasing epsilon and calculating the link density and plotting them. So here also we find there are two scaling regions for ECG data, unlike other chaotic systems. And these two scales in a way can be calculated. The scaling indices or the slopes of the curves can be calculated. And if you say that the link density is going as epsilon raised to gamma, gamma has two values, gamma 1 and gamma 2. And then we find this capital gamma, which is measured as the difference relative to one of them, gives you a better indication or better index for classifying healthy data for different diseases and differentiating them with standard chaotic systems. So this is a new index that we have introduced, which will help you to identify different types of data sets. Now, earlier research that I showed up to this for ECG data in recurrence networks was using only one of the channels, which is channel 2, which is closest to the heart. But actually there are 12 channels for normal ECG data. 6 of them are very close to the heart. So earlier multifractal measures we have done for all the 6 channels. Now we try to check whether there is any relevance in doing that for recurrence network also. And we find that there can be variations from channel to channel. And these variations also can be an indication of the nature of the healthy state of the heart. So for example, this is for normal people in 2 channels. This is for bundle branch block. You see, channel to channel, the variation is very, very impressive or very prominent. So how do we capture these variations? For that, what we do is we generate a multiplex recurrence network from the ECG data. So every channel, one channel gives you one network, next channel gives you another layer of the network, next one another layer, like that. And then we connect them in a multiplex mode because they have a time sequence. So we want to keep that time sequence. The ith point here is automatically connected to the ith point here. That is how we connect them. And they have different structure on each layer. So this is how you connect a construct a multiplex recurrence network. This is called a supra-adjacency matrix. Because we have I-to-I connection, all these non-diagonal sub-matrices will be identical, but there is a diagonal matrix here which gives you the structure in each layer of the network. And there are a large number of measures that we calculate to understand the similarity between the layers as well as the dissimilarity between them. Some of them are average measures. For example, edge overlap. We can check how much overlap is there between the measures in each layer by calculating a measure like this. And of course, from the degree distribution, we can check the degree distribution of each layer and how similar or dissimilar they are. So one way is to calculate the cosine similarity, which is used here. So what we do is we take the value of the degree in each index, each layer. Here it is L1 here, L2 here, and then we calculate something like a cosine angle. And the mutual information also can be calculated. Now, how the distribution of local clustering coefficients are. So their index of dissimilarity is captured by this, and their similarity is captured using the normal Pearson correlation coefficient. So these are some of the quantifiers which are normally can be used for multiplex recurrence network. Here our basic idea is to understand whether channel to channel variations are there, and if it is there, is it an indication of a disease or not. This is the average values that are plotted. This is the average link density and the average edge overlap. Each point here corresponds to one data, and the healthy ones are all shown in green and different diseases are shown in different colors. And the size of the dot is the variance in its edge overlap. And then we see that variance can change. Variance is proportional to the variance in the link density. That is what is shown as the size. So across the layers, we can see there are differences. This is for the link density versus edge overlap. This is the average link density versus average clustering coefficient. So these average measures, how do they differ from each layer to layer for each data sets? So for healthy, we see that the spots are not very big in size, which means the variance is small. But for different diseases, there is a size which indicates that there is some difference. And also, most of them lie correlated along a line. These two are correlated. And especially for the healthy one, it is highly correlated values, this edge overlap and link density. But there is disproportionate variations in unhealthy conditions. This is one way of let us say, display the difference between the measures. Another way is to go ahead and calculate all of them for all the data sets, show them as a distribution points here, average value plus standard deviation. That way, you can actually show them for different pairs of layers for all the data sets. So if you have 6 channels like that and 6 layers in the multiplex recurrence network, you can have 15 combinations of pairs of layers. For each one of them, you can calculate these indices, which will again tell you how the variations are across subjects of a category. This is the other two, correlation coefficient as well as index of dissimilarity. That also we can display. But to make sense out of it, it is very important to calculate some index, the statistical significance of these results. This is required because the size of the data sets in the healthy and the other one may not agree. Disease cases may not agree. That is one thing. and whether there is any significance in saying that the distribution of points for one set, which is a disease set, is different from the normal one or healthy one. Does it make sense? So for this, we use the statistical significance measure called the p-value, and that is plotted as a matrix here. So significance of all the computer measures I am showing here. This is for cosine similarity and the mutual information of each disease compared to the healthy. So the p-value very, very small means it is very significant. White means insignificant. And below value 0.05, we are showing some stars. So green is more significant and blue is less significant, like that. And if the value is very small, that means it is highly significant. So this will tell us which layer has problem or difference with the normal case, and how we understand whether it is a localized difference or overall affecting the spatio-temporal dynamics of the heart. So in this study, since we are dealing with all the 6 channels from different locations in the heart, we are treating the whole dynamics as whole heart as a spatio-temporal system and trying to understand the underlying spatio-temporal dynamics of the whole heart. Therefore, how it varies from location to location is important, how it changes for healthy people and for unhealthy people. This is for the other 2 measures, same type of quantification. So this is some of our conclusions from that. We find that in the bundle branch block, there are isolated elements in all these measures, which indicates that the difference is localized. So some layers are more affected than the others. On the other hand, this cardiomyopathy shows a gradual change. Dysrhythmia is green in all measures. Myocardial infarction also significant difference is seen from multiple places. So this is closest to the healthy, so it is not a localized disorder, but does not seem to affect the spatio-temporal dynamics. So by this type of analysis, we can understand overall pattern of dynamics that is changing when you have a particular disease. So far, we talked about understanding the system. I think I have some more time, Sendrinel.
Yeah, you can go 10 more minutes.
10 more minutes, okay, thanks. So now we will see how the same quantifiers can be used for understanding the dynamical transitions. So for this, what we normally do is a moving window analysis. So if you have a lengthy data, what we do is we split it up into windows and then slowly slide the windows. So for example, if you have some 10,000 or 20,000 points in the data, we take 2,000 points because you want to construct recurrence network, even 2,000 points are okay, as was first window. Then shift it by 100 points. So that means you are moving now window from 100 to 2,100. Again, window size is the same. It is shifted by the same points like that. This is called a sliding window analysis or moving window analysis. So by doing this, we can understand any dynamical transitions are happening in the system, because most of these quantifiers that we discuss now will change its value when a dynamical transition is happening, because the nature of the trajectory itself is changing, the underlying dynamics is changing, so we should be able to understand that. So this we are showing for a typical case for a transition that happened in a star called Betelgeuse. So they found that this star, which is in the Alpha Orionis, this is the Tiruvadira Nakshatra we talk about. It's a red star, which is actually seen with the naked eye also. But around 2019, this star underwent a major dimming. That means its intensity went down. So how do you understand that as a dynamical transition? Is it a dynamical transition? If so, is there any indication of that transition going to happen, which we call as the early warning signal here? Is it possible to do that? This is something which we have done. So what we did is we construct the recurrence plot out of it. This is the data and this recurrence plot out of it. And we wanted to see how these recurrence quantifiers change over time. So with the windowing analysis, we are plotting this determinism measure we talked about and the laminarity measure. And we find that in all these cases, there is an increase. Just before the dimming, there is an increase in these values. So this increase in these values actually correlates with the other measures of early warning signals like the autocorrelation, variance, etc. And then later studies also support that there is a change in the periodicity and the pulsational dynamics of the star, which indicates a change in the underlying dynamics. So we could say that this will be able to predict the dynamical transition in the system. So this type of dynamical transitions one can understand. Right now, I have a student working on the financial crash of 2008, where we do this moving window analysis and try to find out whether there is that crash actually corresponds to a change in the dynamics of the system. Similarly, for climate data and temperature data, we are trying to find out whether global warming around 1955 is around that period is the global warming started. So we can check and find out whether global warming has affected the dynamics, or it's just temperature going up, that's all, or is there a change in the dynamics of the underlying system. These are some of the things that we can do with this type of measures. So let me summarize. So we have seen how we can construct a phase space trajectory from a given data using delay embedding and Reuel-Takens method. And once you have got the trajectory, we can characterize its dynamics, that is nature of the dynamics. First of all, we can say it's a periodic system, it's a noisy system, or is it a chaotic system, hyperchaotic system. All these things we can identify. Is it strange non-chaos? All these we can identify. And then how do we characterize the dynamics? For that, we use these multifractal measures. We have seen how to compute them. And from the multifractal measures, especially these 4 indices, 2 gamma values and 2 alpha values together can characterize the multifractal spectrum and tell you something about the dynamics. And if your size of the data is not big enough to do multifractal analysis, you can always do recurrence analysis. You take recurrence plots and recurrence network, and then from the reconstructed trajectory. And measures of network can be used for classifying the data sets. We have seen how we have used it for classifying the binary stars, different cases of ECG, and then climate data. And then we have also seen how new measures like heterogeneity measure, weighted network, and new features of this like bimodality and scaling helps us to classify them further or to understand their dynamics further. And if you have a set of data coming from the same complex system, like the heart, one can even do it for the brain. We have EEG data from different locations in the brain. All of them together can be taken and analyzed as a single spatio-temporal system. And then we can do it by using a multiplex recurrence network analysis, so that we understand the similarity between each data and the similarity as well as the dissimilarity, which will tell us the locations in that system, whether they are different from a different location, etc. So basically that will fully characterize the underlying spatial temporal dynamics of the system. That's what we have seen. Now, we also saw that by doing a sliding window analysis, we can check or look for dynamical transitions that happen in the system. So, for example, some cases where some transitions are critical, or we call them tipping, that means sudden transitions that happen in the system. I remember 1 or 2 lectures you had on this type of transitions or tipping in the dynamical systems. So in such cases, we can see that by collecting the data from the system, can we have some measures and see whether those measures will give us some indication of the dynamical transition that is going to happen in the system. This will be an interesting one, which will have lots of practical applications, because predicting a sudden transition will help us quite a lot to avoid unpleasant results of that transition, or even to understand what is happening to the system, like the star case that we have discussed. So with this, let me conclude. These are some of my collaborators. This work actually that I presented comes from, let me say, around some 20 years of work I have comprehensively I have projected. Now, Hari Krishnan in Cochin College and Renji Mishra in IUCAP Pune, we have long-standing collaborations of over 22 years. And Amatkar from PRL Ahmedabad has collaborated with me in characterizing multifractal spectrum, etc. Then Ringu in RSET Cochin, Snehal in Pune, is Pune University. These are all some of my earlier collaborators, and now they are faculty members. And Sandeep now is doing a postdoc in University of College London. We collaborated in binary star work. Sneha is actually working with me. She is now submitting her PhD thesis. She worked at multiplex recurrence network analysis of ECG data, etc. And Vedartha worked on some financial data with me long back in ISER Pune. Right now he is a faculty in University of Tübingen. And some of my other collaborators are students, Yamini and Ame, who are project students from ISER Pune. Jayesh and Uttara from ISER Tirupati, and Krishna Das is still working with me from Cochin. Some of the data he is working with me. With that, I thank you. And if there are questions, I'll be willing to, I'll try to answer.
Yeah. It's time for questions.
Shall I stop sharing or wait?
Yeah. No, you don't need. Don't stop staring. So some people might raise questions.
Okay. That's okay.
Okay. Thank you very much, Ambika, for a very impressive presentation of your work spread over 3 decades. I really enjoyed your talk.
Thank
So
you.
I have some general questions. So suppose if you take the ECG data, a doctor, suppose a patient comes and so he takes ECG data. So how will he utilize this data to understand what is happening? I mean, can he identify an early warning signal that something?
See, for ECG data, we have not done this early warning signal approach. So that person is going to have a heart attack or something. So for that, the reason why we couldn't do it is we want the data from a normal person from early days, and then he should be undergoing treatment or he should be going towards a heart problem. That type of data normally they don't keep in the hospitals. We checked in some hospitals in Pune also. Normally, when you are in normal condition, nobody goes to a doctor and takes an ECG unless we have some annual medical checkup or something. So it is very difficult to do in the case of ECG. But from the theory, from our understanding of this, what we have done, I feel it is possible because we want to have a continuous monitoring of the data. Then only we can say whether there is, for example, if somebody is in ICU unit doing Holter data, and overnight while lying there, he develops a heart problem, then certainly we have a 24-hour data where we can use the sliding window and predict that. Otherwise, in the context of ECG, lack of data is the reason why this is not possible. Because you see, from person to person, normal condition itself is different. So you cannot compare a person, diseased person with another normal person's data and make a measure. That's a problem. Am I clear? I think you are muted, no?
Able to hear me?
Yeah, now you can hear you. Yeah.
Yeah. So any person who has some doubt about his heart problem, he goes and have a checkup. So he will have an ECG data, and the doctor finds there is nothing wrong. But after some time again, he goes there and there is some more complications. So is it not possible to use?
If you have that successive data, see, actually, this analysis will help in actually monitoring a patient also. Because normally nobody goes to the doctor before a problem. But if he goes with a problem, how he progresses in that disease, either he is becoming worse or improving. So like progressive clinical analysis understanding can be done. But if you have the data like that, certainly we can try that and find out.
The point I'm trying to stress is that having so many statistical measures,
yeah,
if you can collaborate with some hospitals or some doctors, that will be very, very helpful.
Yeah, that's right.
In due course.
And also, one can develop an algorithm and put it through machine learning or something like that. Then it becomes automatically, it will do it.
Yeah.
That is possible. That's actually a good solution. Yeah,
that is one thing. The other another question I have is, so you have, for example, measures on this astrophysical data.
Yeah.
So what does it imply? So you say that you can associate with complex networks or multiplex networks and so on.
Yeah.
So when you say such network, so the light coming from a particular star and so on. So does that mean that the different parts of the star are interacting and giving rise to this particular light?
Yeah. So actually, what we measure for the star is the magnitude of the intensity.
Yes.
So it's an overall thing. But there are results which show that this is related to the radius of the star. So the star is expanding or contracting. It is sometimes pulsating, doing it periodically, but not exactly periodical. And sometimes most of the stars, they have a chaotic type of oscillations also. So we are able to say that because most of these stars, they don't have a real set of differential equations quantifying their dynamics. So in such cases, by looking at the data, we are able to say the state of dynamics of the star. For example, a star is period doubling. For example, this Betelgeuse people say it has undergone a change in its pulsational dynamics. So like that, change in the dynamics can be picked up because astrophysical data, normally we get long data over long times. Such changes can be identified. And also, as I have shown, we can classify them. Which are
Yeah,
these?
but does that mean that that the different parts of the star are interacting in such a way they give rise to this
Correct.
total intensity?
That is right. Yeah, because when you actually try to understand its dynamical processes and all, it's mostly turbulence, and therefore it is something like a sort of partial differential equations or something. So in a way, we are saying by network measures, we are trying to see how the interaction between the different parts give to an emergent behavior in the star. Correct.
Very nice. Okay,
Yeah.
thank you very much. Thank you.
So, any other question from the audience?
Ma'am,
Yes. Yes. Please raise your question.
ma'am, while calculating the false needed neighbor, we are fixing some value called alpha. How to fix the value?
See, this alpha, normally we fix it by experience. What we want is the value, it cannot be, we cannot say that there should not be only very small difference. Because even when you have the correct dimension, when you go to the next dimension, a small change can happen between the points. But if the value is very significant, then that means it is false. So normally for every data, this we do by experience. So there is a way of quantifying that, just choosing that as some value and then try to do it, and then we change it and see whether this value result that you get changes very much. This is one way of checking, because we want a large enough values for alpha so that we know which are the false neighbors. If you take a very small value, all of them may look like false neighbors, which is not true, no? So this is in a way slightly trial and error. Each data set, you should understand them, do all these trial and error methods, and then quantify them.
Okay, ma'am, tell me more about data binding.
Pardon?
Tell me more about data binding.
Data?
Binding.
Binning. So binning, why we do is normally one level of noise elimination can be done using binning itself. Because small variations due to noise in measured noise, for example, measurement noise or instrument noise, can be avoided by binning. So what you do binning is you have a large set of value for corresponding to every time interval. Let us say you have a value. Sometimes this measured data may have some gaps. They will not be equally distant in time, because it is some sort of measurement data. So it may not be exactly, let us say, suppose the time step between two measurements is 0.1. Every 0.1 distance there may not be. So when those things we say are gaps in the data. So the gaps in the data also can affect your results. But if by binning, to some extent it can be avoided. So suppose you have values like 1, 2, 3, 4, etc. First 1 to 5, you take as your bin size as 5. Then first 5 points in the data, you average and replace it as the first value. Next 5 to 10, that 6 to 10 values, that you take as the next bin. Take all the average of those 5 values, replace it as your second value. So the size of the data will reduce by binning. But the bin size also depends on the nature of the data. You can try with the size equal to 5 or 10. If you have a large data, you can even think of a bin size which is equal to 10 or something. So the size will reduce, but then small variations due to noise, etc., and due to data gaps can be avoided by binning. Is that clear?
Yes, but this is somewhat similar to making a time series very different.
Oh, I can't hear.
Yeah, he is sitting near to me. I will ask him.
Yeah.
He is sitting in the next room. So I'll ask him.
Making the stationary by differencing from one time step to another time step.
One time step to another time step I heard, but before that, whatever you said, I didn't hear. Can you type in the chat?
Yes, ma'am.
Yeah.
So any other question? I think others are hesitating. I will ask them to write if they have any doubts.
Right. If there is anybody writing in the chat, or later also they can email me.
Yes, madam. So I want to wind it up now. So thank you, Professor, for delivering a wonderful and very interesting talk. It's really a summary of 10 years work. Unbelievable. I believe that the student might have understood the importance and applications of data mining in dynamical systems. I hope they will write to you some doubts. Okay. With that, I want to wind up.
Okay.
Thank you, madam. Thank you. Thank you very much. I will write to you, madam. I will write to you.
Thank you, Professor Senthilvelan, and thanks to all of you for listening to my talk. Thanks.
Thanks.